Hello, everyone, and welcome. Today, we're going to dive into something that's really at the heart of how computers work: memory organization. We're going to uncover how your machine cleverly manages all its resources, and we'll do it using a simple but really powerful analogy. So, have you ever really wondered about this? I mean, how on earth does your computer run a heavy game, a web browser with a dozen tabs, and a music app all at the same time without just crashing? The secret isn't just about pure power. It's actually an incredibly smart system of organization, kind of like a perfectly run library. And that's the exact mystery we're going to solve together today. Okay, so here's our plan for today. First, we'll get familiar with this idea of the computer's memory library. Then we'll look at the main bookshelf. That's RAM and ROM. After that, we'll uncover the real secret to speed: cache. Then we'll see how computers pull off this amazing trick of having what seems like infinite space. And finally, we'll look at how they talk to the outside world. Sound good? Let's get started. All right, section 1, the computer's memory library. So let's start building our main analogy. I want you to imagine that your computer's CPU is like a really hardworking student, cramming for a big exam. Now, to study well, this student needs information, and they need it fast. But where does all that information live? Well, it's all stored in the memory, which for our story is going to be a massive university library. And here it is, the big picture. This pyramid you're looking at is called the memory hierarchy, and it's absolutely key. The whole idea is just like in a real library, right? The stuff you need most often, you want it right next to you. So at the very top, closest to our student, the CPU, we have the fastest, most expensive, but also the smallest memory. And as we go down the pyramid, the memory gets much, much larger and way cheaper. But, and this is the important part, it also gets a lot slower. It's all a game of trade-offs. Okay, so let's make this crystal clear. Let's map our tech terms to our library story. Number 1, the CPU, that's our hard-working student. 2, the cache, that's the small study desk right in front of them, holding just the most crucial notes. 3, the main memory, that's the bookshelf right next to the desk, with all the books for the subjects they're studying right now. And finally, number 4, auxiliary memory, like your hard drive, that's the huge library archive down in the basement. It holds everything, but man, it takes a while to go down there and get something. All right, next up, your main bookshelf. We're going to zoom in on that bookshelf right next to our student's desk. This is our main memory, and it's really made up of 2 super important types: RAM and ROM. Let's break this down. Think of RAM, random access memory, like the textbooks you borrow from the library. You can use them, write notes on them, but when you're done studying for the day or you shut down the power, poof, those books are gone. They have to be returned. That's what we mean by volatile memory. Now, ROM, read-only memory, is totally different. It's like the official library rulebook. It's bolted to the wall, it's always there, you can't change it, and it has the most basic instructions on how to get started. That makes it non-volatile. So what's written on the very first page of that permanent rulebook, that ROM? Well, it's a special little program called the Bootstrap Loader. Its one and only job is to give the whole computer a kickstart when you hit that power button. It's the instruction that tells the computer, hey, wake up. Go down to the library archives, the hard disk, and load up the main operating system. And just to make things a little more interesting, even RAM itself comes in 2 main flavors. First, you've got SRAM, or static RAM. This stuff is incredibly fast, but also really expensive. The best way to think of it is like sticky notes for quick, urgent reminders. Because it's so fast, we use it for cache memory. Then you have DRAM, or dynamic RAM. This is a bit slower and much cheaper. It's more like the main notebook you're writing all your detailed notes in. And this is what we use for our main memory, our bookshelf. Okay, let's pause for a quick check-in. So which type of memory is volatile, but is also essential for starting the computer? This is a bit of a tricky one, right? The process starts with the non-volatile ROM, where the Bootstrap Loader lives. But the moment that's done, the computer absolutely needs its volatile RAM to act as a workspace to actually load up the operating system. So you see, they both have their own crucial part to play right at the start. Okay, moving on to the real secret sauce of modern computing speed. It turns out being fast isn't just about having a massive bookshelf. No, the real magic is in having a small but incredibly smart study desk. And that, my friends, is our cache memory. Now, the whole reason cache even works is because of a cool principle called locality of reference. I know, it sounds fancy, but it's just a term for describing a student's normal study habits. There are two types. First, temporal locality. That's when you keep rereading the same important chapter again and again. And then there's spatial locality. This is the idea that if you just read one paragraph, you're probably going to read the very next one. And it turns out computers work with data in the exact same way. So how do we know if our study desk is actually doing a good job? We measure it with something called the hit ratio. It's super simple. A hit is when our student, the CPU, needs some info, and yes, it's right there on the desk, in the cache. A miss is when, oh no, they have to get up, walk over to the bookshelf, and grab the book from RAM. The formula is just hits divided by the total of hits plus misses. Basically, the higher your hit ratio, the less time you're wasting, and the faster your whole system runs. Now prepare for a little bit of magic. What if your study desk was so incredibly smart that you didn't have to remember where you put a specific note? What if you could just think about the content like, I need that formula for thermodynamics, and the desk would instantly give you the right note? Well, that's exactly what associative memory, or CAM, does. It's a special type of memory that searches by what's in it, not by its address. This makes finding things unbelievably fast. So let's lock this in. To improve performance, do we want a higher or a lower cache hit ratio? Of course, we want it as high as possible. The more hits we get, the more time our CPU spends actually working, and the less time it spends waiting around for data. Simple as that. All right, on to our next section, the illusion of infinite space. And this is where we talk about a truly brilliant trick. Think about it. How can your computer run a massive program, like a huge modern video game, that is way, way bigger than the actual physical memory, the RAM, that you have installed? How is that even possible? Let's go back to our student. Imagine this, their bookshelf. The RAM is completely full, but they just got an assignment and they need another book, a big one, that's stored way down in the library archives, on the disk. So what do? They can't just start throwing books on the floor, right? There's no more space. This is where our hero, the magic librarian, comes in. In the real world, this is the Memory Management Unit, or MMU. When the student, the CPU, asks for that new book from the archives, the MMU jumps into action. It looks at the bookshelf, finds a book that hasn't been touched in a while, whisks it back to the archives, and then places the newly requested book right in that empty spot. And this whole swap happens so incredibly fast, our student, the CPU, has no idea it even happened. It just continues to work, living in this beautiful illusion that it has a bookshelf of infinite size. That, in a nutshell, is virtual memory. So, quick recap question. What is the main purpose of virtual memory? Simply put, it's to let us run programs that are much larger than our actual physical memory by creating that clever illusion of infinite space. Okay, final section, talking to the outside world. So our library is all set up and organized, but how does our student actually get new books from the archives or send messages to the outside world? Well, this is where input/output, or I/O, and DMA come into play. So there are basically three ways our student can get books from the archives, each one smarter than the last. First, you have programmed I/O. This is like the student constantly running to the librarian and asking, is it here yet? Is it here yet? Is it here yet? Super inefficient, right? Then we get a bit smarter with interrupt-driven I/O. Here, the student goes back to their desk and studies, and the librarian just taps them on the shoulder when the book arrives. Much better. But the absolute best, the most efficient way is direct memory access, or DMA. This is like the student giving a list of books to a special assistant, the DMA controller. This assistant does all the work, gets the books, puts them on the bookshelf, and never disturbs the student. The student can just keep working completely uninterrupted. Genius! Okay, final question for this section. Which I/O method is the king of efficiency, allowing data to move between memory and devices without ever bothering the CPU? You got it, it's direct memory access, or DMA. Now, I know what some of you might be thinking. Okay, this is cool theory, but why does this really matter for my future? Well, listen up, because this is so important. These ideas aren't just theory, they are the absolute bedrock of all modern technology. If you're excited about AI and machine learning, you have to understand this stuff to handle the massive data sets needed to train models. The entire cloud, AWS, Google Cloud, it's all built on these concepts of virtual memory. And all those small IoT and edge devices, for them, efficient memory use isn't a nice to have, it's absolutely critical for them to even work.
Trust me, mastering these fundamentals opens doors to every single exciting field in technology today.
And that brings us to the end of our journey today. We've walked through the entire computer's memory library, from the deep archives right up to the student's busy study desk. But of course, technology never, ever stands still. So I want to leave you with one final question to think about. As the amount of data in the world just explodes and our processors get ridiculously fast, what do you think the next level of this memory library is going to look like? What's the next big invention in memory organization? Something to chew on. Thank you